In this class, you'll break through the mystery of Arduino programming. You'll learn how to think like a coder, how to use variables to store data, constants for fixed values, arrays for lists, and how to make your code smarter using conditionals and logic. You'll also dive into loops, functions, and the arithmetic and logic operators that bring everything together. By the end of this lesson, you'll no longer be just wiring components, you'll be programming with confidence. And yes, as always, there is a hands-on project waiting for you at the end to practice everything you've learned. This is lesson 6 of a 24-part series called Arduino for Beginners. If you haven't watched the earlier videos, I really recommend going back because each class builds on the last one. Alright, let's get started. This video is sponsored by DF Robot, the provider of the Mind Plus Arduino coding kit, the same kit we've been using in every project so far. It comes with sensors, modules, jumper wires, and an input-output expansion shield. Everything a beginner needs to master Arduino from scratch. You'll find the link of DF Robot store in the description. Now, let's talk about how to actually write your own programs. Let's start our explanation by analyzing one of the most fundamental concepts in programming: variables. Imagine your Arduino sketch is like a recipe, and just like a recipe needs to remember how much flour or sugar to use, your program needs a way to remember numbers, words, and other values as it runs. That's where variables come in. A variable is like a labeled box in your Arduino's memory. You can store a value in it, change it later, and use it throughout your program. For example, want to remember which pin your LED is connected to? Use a variable. Want to keep track of how many times a button has been pressed? Use a variable. In short, variables allow your program to store and manipulate data, and that is what makes them one of the most essential building blocks in coding. Another reason that makes variables so important is that they allow you to change information on your code in a simpler way. Imagine if you had to write the same value, say pin number 9, dozens of times in your code. What happens if you later move your LED to pin 6? You'd have to update every single line manually. That is not only a pain, it also leads to bugs. But if you use a variable, let's say int LED pin equals to 9, now you only need to update one line. Everything else just works. Clean, reusable, and flexible. Now that you understand the concept of variables, let's learn about variables types. Not all values are the same. Some are whole numbers, others are decimal numbers. Some are just true/false. To handle all these different types of data efficiently, Arduino gives you different variable types. Here are the most common ones you'll use. Int. For whole numbers like 5, -12, or 1000. Float for decimal numbers like 3.14 or -0.001. Bool for true or false values. Perfect for things like is the LED on? Char for a single character like A, B, or 7. You may be wondering, why do these types exist? In short, because microcontrollers like the Arduino have limited memory. For example, a float, which stores decimal numbers, usually takes up more memory than an int, which stores whole numbers. So even though you can store a number like 1 as 1.0 in a float, it's better to use an int if you don't need the decimal. You can refer to the official Arduino documentation for more details about this topic. Here's how you can declare variables on Arduino IDE. We just talked about the variables, but sometimes you don't want a value to change. That's when you use a constant. Let's say you write int LED pin equals to 9. This works, but the value can still be changed later in the code, even by accident. LED pin equals 5, for example. But if you write const int LED pin equals to 9, now the Arduino will protect that value. If you or anyone else tries to change it later, the code won't compile. You declare a constant by using the const keyword before the data type, as you can see here. You can use const with any variable type. Some people also use all caps for constant names to make them easy to spot. This is just a style preference, but it can make your code easier to read. See the following example. In this example, we used constants to define pin numbers. These values won't change, making the code safer and easier to debug. Using const isn't just about memory, it's about writing clean, dependable code. So far, you've seen how to use variables to store a single piece of data, like a pin number or a temperature reading. But what if you had to control 5 LEDs connected to different pins? You could create 5 separate variables. That works, but it's messy. And if you wanted to turn all those LEDs on or off in a loop, you'd have to repeat your code 5 times. That's where arrays come in. An array is like a row of boxes, where each box holds one value and all the boxes share the same name. Instead of 5 variables, you can write the following. Now you have one variable, LED pins, that stores all 5 pin numbers in one place. As you may notice, arrays are super useful because they let you group related data together, write less code, access items using an index number. This makes your code shorter, cleaner, and easier to manage, especially as your projects get more complex. Now let's take a closer look at how array works. Each item in an array is stored at a specific position, starting from 0. So in this example, 3 is in position 0, 5 is in position 1, 6 is in position 2, 9 is in position 3, and 10 is in position 4. If you try to access LED pins 5, it won't work because there is nothing stored there. Arrays are zero indexed, which means they start counting from 0, not 1. You can also read or update array of values like this. Arrays unlock a whole new level of scalability and organization in your code. Once you get comfortable with them, you will start using arrays in almost every project. We talked a lot about data. Let's move on and learn about other coding structures. Imagine your Arduino is faced with a decision. If a button is pressed, turn on the LED. If temperature is too high, activate a fan. If it's dark, turn on a light. These decisions, if this, then do that, are called conditionals. In code, conditionals let your Arduino react to the world around it by checking whether something is true and doing something based on that. Without conditionals, your program will do the exact same thing over and over again, but with conditionals, it can make choices. The most basic conditional is the if statement. It looks like this. The condition is something that can be true or false. If it's true, the code inside the curly brackets runs. If it's false, your Arduino skips it. For example, this means if the button is pressed, turn the LED on. But what if you want to do something different when the condition is false? Then that's where else comes in. In this new code, your Arduino says, if the button is pressed, turn on the LED, otherwise turn it off. Sometimes we need to check multiple conditions. That's where else if is useful. This creates a chain of decisions where only one block runs depending on the situation. As you may notice, in the previous examples we used some special symbols inside the conditional structure, like equal to or greater than. These symbols are known as comparison operators. When you write a conditional like if x equals to 10, you're asking your Arduino to compare two values. To do this, we use comparison operators. These are symbols that help your program answer questions like, is this equal to that? Is this greater than that? Is this smaller or different? Each comparison returns a true or false result, exactly what an if statement needs to make a decision. Arduino doesn't understand plain language. You can't say check if it's hot. Instead, you must use math-style comparisons that it can evaluate. For example, if temperature is greater than 30. This reads as if the temperature is greater than 30, then. Without comparison operators, you couldn't write conditionals that depend on sensor values, time, counters, or anything dynamic. They are the core of logical decision-making in code. Arduino has 6 comparison operators. Refer to this table on screen for more information about them. An important note, don't confuse WICO to WICO. That means WICOs to. WICO, one symbol, is for assigning values. WICO, two symbols, is for comparing values. For example, x equal 5, set x to 5. And x equal 5, check if x is equal to 5. Every time you use if, your condition must return true or false. Comparison operators are the tools that allow you to ask questions in code. Is this button pressed? Is the temperature above a threshold? Has 10 seconds passed? These questions are the logic behind every smart behavior your Arduino performs. By understanding comparison operators, you are learning how to give your code the power to decide, and that is a major step toward real programming. Now let's look at another type of operators, the logical operators. So far, we've written conditionals like. But what if you want to check two things at once? For example, if the temperature is high and the humidity is low, turn on the fan. If the button is pressed or the motion sensor is triggered, sound an alarm. This is where logical operators come in. They let you combine multiple conditions into a single decision. These commands are important because real-world situations are rarely based on just one condition. Logical operators let your Arduino handle compound logic, just like we do in everyday thinking. There are 3 different logical operators. You can refer to this table for more details. Let's look at each operator, starting from AND. This is only run if both conditionals are true. Now the OR conditional runs if at least one of the conditions is true. In the end, we have the NOT operator. It reverses the result of a condition, so false becomes true and true becomes false. This means if is light on is false, then turn on the LED. You may be wondering how it all comes together. Let's say you are building a smart fan controller. Here we are saying turn the fan on only if it's hot and someone is in the room. Otherwise, turn it off. Logical operators allow your Arduino to make smart decisions based on multiple inputs, just like we do in real life. A tip: when combining conditionals, especially with AND and OR, use parentheses to make the logic easier to read and avoid confusion. This reads as, if it's dark or nighttime and there is motion, turn on the lights. Logical operators are the bridge from simple logic to real-world intelligence. They let your code ask complex questions and act only when the right combination of conditionals is met. Congratulations if you made this far. There are only 2 coding structures left to study, loops and functions. But before I dive into these advanced topics, let's take a look at the last type of operator we need to know, the arithmetic operators. In the same way that you use math in everyday life, adding prices, calculating time, subtracting scores, Arduino also needs math to process data and control behaviors. Arithmetic operators are the basic math symbols your Arduino uses to perform operations on numbers. They help your code do things like add values, subtract quantities, multiply measurements, divide results, and find reminders. You use arithmetic operators all the time in your Arduino programs. For example, want to fade an LED gradually? You increase or decrease its brightness by using plus or minus. Want to track how long something has been active? You accumulate time using plus equal. Need to alternate between even and odd steps? You use module to check reminders. Math is the language that lets your Arduino make precise, continuous changes, not just on-off decisions. There are 5 different math operators you should learn. Refer to this table for more details. Let's explore each of them briefly. Number 1. Addition. Adds two values together, used for increasing counters, combining values, etc. Number 2. Subtraction. Subtracts one value from another, useful for countdowns or adjusting values over time. Number 3. Multiplication. Multiplies two numbers, handy for calculations involving size, timing, scaling, etc. Number 4. Division divides one number by another. Note, if both numbers are integers, the result will be an integer. If you want a decimal result, use float. Number 5. Module returns the remainder of a division. This is useful for checking even odd numbers or cycling through a partner. You can also combine math with assignments to simplify code, as you can see on this table. We can combine all we learned so far to write a fading LED script. After uploading this to Arduino, we have arithmetic operators are more than just math. They are how you make your Arduino count button presses, calculate sensor averages, create visual effects, manage loops and conditions, and much more. They are the foundation of every dynamic behavior in your code. We are reaching the end of this lesson, but before saying goodbye, I need to teach you a very important concept in coding: loops. They will help us to repeat tasks automatically. In real life, we often repeat tasks, brushing teeth, blinking, checking the mailbox every day, etc. In programming, loops let us automate repetition. Instead of writing the same code over and over again, we write it once and tell the computer to repeat it as long as needed. Arduino programs usually run non-stop from the moment the board is powered. That is why the loop function exists, to repeat your code endlessly. But inside a function, you can use different types of loops for different kinds of repetition. Let's go over the main ones. Firstly, let's learn the for structure. A for loop is great when you know exactly how many times you want to repeat something. For example, blinking an LED 10 times or checking the first 5 elements in an array. Its basic structure is something like this. As you can see, we defined a special variable, a counter. This code can be interpreted as the counter I starts at 0 and while I is less than 5, keeps adding 1 unit to the counter. In reality, this for loop will execute the code inside the curly brackets 5 times. We can use it, for example, to blink a LED 10 times. Another loop Arduino supports is the while structure. Use a while loop when you want something to repeat until a condition becomes false. The basic structure is now, a very important note: if the condition is always true, you will create an infinite loop, which may freeze your program. Always make sure the condition will eventually turn false. The blink a LED 10 times can be represented using while this way. As you can see, some things changed. The int I equals 0 initialization was moved before the loop. The I++ increment was added at the end of the loop. The condition I less than 10 remains the same. Despite the changes, the result is exactly the same. The LED blinks 10 times. There is a third and last loop structure we are going to understand. It's similar to the while loop and is called do while. This loop works like while, but it always runs the code at least once before checking the condition. The structure is, for example, in this code, you read values from a 0 and keep doing it until it becomes less than 100. Now you may be thinking, how do I choose the right loop structure? Well, if you know exactly how many times to repeat, choose for. If you want to repeat while a condition is true, choose while. If you want to always execute once, then keep going if needed, choose do while. Loops are important because they allow your Arduino to read sensors continuously, update displays regularly, blink LEDs in patterns, monitor inputs in real time, repeat actions without copying code. Without loops, your Arduino would only do something once and then stop. And that is not what we want in an embedded system designed to run forever. The last structure we will study today is functions. A function is a block of code that performs a specific task. You can call it whenever you need to do the task, instead of writing the same lines over and over again. Think of it like a recipe. Once you write it down, you can follow it whenever you want a dish. No need to rewrite the whole recipe every time. In Arduino, you've already used two special functions setup, and loop. But you can create your own custom functions too. These structures are important because it helps avoid repetition, write once, use many times. It makes your code easier to read. It's easier to understand what Blink LED does than to read 5 lines of blinking code repeated all over the place. It keeps things organized. Split your code into logical parts. Here is the basic structure of a function. Return type, what the function gives back. For example, int, float, or void if it returns nothing. Function name, the name you choose for a function. Parameters, inputs the function needs. These are optional. Let's transform the Blink LED example in a function. This code is a bit confusing when you look at it for the first time, but I'm going to break it down. Void means the function doesn't return any value. It's just doing something, in this case blinking an LED, but it won't give anything back. Blink LED is the name of the function. You can call it later in your code to make the LED blink. Int times and int delay time are parameters, values you pass to the function when calling it. Times gets how many times the LED should blink. Delay time gets how long the LED stays on and off in milliseconds. So this function not only lets us blink an LED, it allows us to set up how many times it blinks and how much time it will stay on or off. For example, if we write blink LED 500, it will blink the LED 5 times with a 500 millisecond delay between on and off. As you can see, we put a for loop inside the function. There is nothing wrong with that. You can combine structures the way you want. Just make sure to follow the syntax rules. Functions can return values. For example, add numbers gets 2 integers, sum them up, and returns the result. So if we call it passing the numbers 4 and 7, we'll get 11. When working with functions, it's important to follow some basic rules. Give functions clear, descriptive names like read temperature, turn on fan, or calculate average. Keep functions focused on one specific task. Try to keep them short and simple. Now that we finished studying about programming, let's put everything together and build a real project. Today, we are going to build an alarm system using an ultrasonic sensor. If somebody gets within 10 centimeters of the sensor, it triggers the alarm. In our case, it sounds a buzzer while a red and blue LEDs blink. This happens for 10 seconds, and after that, the system resets and starts monitoring again. For this project, you need the following materials. Note, all of them come with the Mind Plus Arduino coding kit. After you get all components, assemble them according to these schematics. Now that you wired up the components, let's recap how the system works. The ultrasonic sensor constantly checks the distance of any object in front of it. If something is detected within 10 centimeters, the alarm is triggered. Alarm runs for 10 seconds. Red and blue LEDs blink alternately while the buzzer sounds. After 10 seconds, the system resets and resumes monitoring. After that, connect the Arduino on your computer using the USB cable. Open up Arduino Cloud IDE and upload the code of today's lesson. It's available on GitHub. Link is in the description. Before uploading the sketch, let's understand how this code works. Number 1. Pin definitions. These lines define constants for the pin's numbers where the components are connected. Red LED is connected to pin 2, blue LED is connected to pin 3, buzzer is on pin 4, trig pin and echo pin go to pins 5 and 6, which are for the ultrasonic sensor. Using const int is good practice because it makes the code easier to read and update. Number 2. Variable declarations. These variables store duration, how long the echo signal takes to return, and distance, the calculated distance in centimeters. Number 3. Setup. In setup, we define which pins are outputs, LEDs, buzzer, and trigger pin, and each is an input. The echo pin receives data from the ultrasonic sensor. This runs once when the board is powered on. Number 4. Loop. Now let's take a closer look at what is happening inside the loop function. First, we prepare the ultrasonic sensor to send out a pulse. To do that, we briefly turn the trigger pin off, wait 2 microseconds, then turn it on for 10 microseconds and turn it off again. This short pulse causes the sensor to emit a sound wave. Then, we wait for the echo to come back. The pulse-in function measures how long it takes for the echo to return. This time duration is stored in the duration variable. Next, we calculate the distance by multiplying the duration by 0.034 and divide it by 2. That gives us the distance in centimeters between the sensor and any object in front of it. If the object is 10 centimeters away or closer, we activate the alarm by calling the trigger alarm function. Finally, we wait a short moment, 100 milliseconds, before checking the distance again. This keeps the system responsive without constantly overloading it with readings. I have a tutorial about ultrasonic sensors here on my channel. I highly recommend watching it so you will be better understand how these sensors work. Number 5. Trigger alarm function. Let's walk through what happens inside the trigger alarm function, the last part of the code. As soon as this function is called, we store the current time using millis. This lets us track how long the alarm should stay on. Then we enter a loop that runs for 10 seconds. Inside this loop, the red and blue LEDs blink alternately while the buzzer stays on. Once the 10 seconds are up, the loop ends and we make sure everything is turned off so the system can return to monitoring. Now that you understand what is happening, let's upload the code and see it working. Additionally, you can create the same code on MindPlus using the block-based interface. I won't dive into the details, but you can refer to this to build your own block code. Also, it's available on the GitHub repository of this series. Link is in the description. And this is the conclusion of today's class. Thank you so much for watching it, and I hope you learned a lot about coding. Don't forget to like, subscribe, and share this video with someone who is trying to learn Arduino coding. Thanks again for watching, and I will see you in lesson 7.